Welcome to a video that will show how to determine a vector-valued function from a rectangular equation. So for example, if we have the rectangular equation y equals 0.5x squared minus 3, as we see graphed here, we should be able to express this using a vector-valued function. The way we do this is express this as a set of parametric equations and then set it up as a vector-valued function. So for example, on this equation, if we let x equal t, we can perform substitution here for x and replace it with t, so we can say that y is equal to 0.5 t squared minus 3. So now that we have the parametric equations for this curve, we can now express this as a vector-valued function where vector r of t is going to be equal to t times the unit vector I plus 0.5 t squared minus 3 times the unit vector j. Or in component form, we would have t 0.5 t to the second minus 3. Now remember, when we express a curve as a vector-valued function, it gives the curve orientation, meaning as t increases, this curve is sketched in a specific direction. So notice that as t increases, x also increases, which means that this curve would be sketched moving from left to right. Again, as t increases, the curve is moving toward the right. Let's take a look at one that's a little bit more involved. Here we want to write the equation x squared divided by 25 plus y squared over 4 equals 1 as a vector-valued function. First, we should recognize this as an ellipse as we see sketched here. The next thing we have to remember is the trig identity that sine squared theta plus cosine squared theta is equal to 1. So using this identity, if we can let x equal some function in terms of t, where x squared over 25 equals either sine squared t or cosine squared t, and then let y equal some function in terms of t, so that y squared over 4 is either sine squared t or cosine squared t, it would then equal 1. So the way we can do that is we can let x equal 5 cosine t. Notice if we square 5 cosine t, we'd have 25 cosine squared t. The 25s would simplify out. And then if we let y equal, since this is 4, let y equal 2 sine t. Well, if we square y, we're going to have 4 sine squared t. This would result in sine squared t. And I'll go ahead and show how this works out. Again, if we have x squared over 25, we square this, we're going to have 25 cosine squared t over 25 plus y squared over 4, that would be 4 sine squared t equals 1. And again, the 25 over 25, the 4 over 4, simplifies nicely, and this is now a true equation in terms of t. So these parametric equations are correct, which make the transition to a vector-valued function pretty easy, where we're going to have 5 cosine t times the unit vector I plus 2 sine t times the unit vector j, or in component form, however, now that it's a vector-valued function, it does have an orientation. So if we let t equals 0, the x component would be 5 and the y component would be 0. So we'd be at this point here, and then at pi over 2, the x component would be 0 and the y component would be 2. So we'd be at here, which means we're graphing this counterclockwise based upon how we defined the vector-valued function. Okay, that's going to do it for this video. Thank you.